In this video, I will be starting the study of confidence interval estimates. I will be starting with the study of the confidence interval estimate for the mean when sigma is known. We know that the sampling distribution of the mean is a normal distribution that can be determined knowing that the mean of all possible sample means is the mean of the population, and the standard deviation is given by sigma divided by the square root of n, when n is the sample size and sigma is the standard deviation of the population. So that means that this distribution have this standard deviation, and the mean, the value in the middle, is the population mean. The initial idea will be of constructing an interval of values for the sample means in such a way that the probability that the sample mean is in this interval is high. We are going to find two values, x1 bar, x2 bar, in such a way that the probability that the sample mean is in this interval is a high probability. That's what we're going to do if we are going to estimate the mean. But if we are going to estimate, for example, the population proportion, we are going to take into account that the mean of all the proportions will be the population proportion. So instead of this mu, we're going to have the population proportion. And the standard error for the population will be a square root of population proportion times 1 minus the population proportion divided by the sample size. But we're going to focus at the beginning what happened or what to do if we want to construct this interval in the case of the mean. As I told you, the idea is to construct an interval in such a way that there is a high probability that the sample mean will be in this interval. And let's say a high probability could be a 95% probability. Because we know that the distribution of the sample mean is a normal distribution, it will be easier to work in the standard normal distribution. So for the standard normal distribution, this mu here will be 0, and this x2 bar corresponds to a value z, and x1 bar will correspond to a value negative z. If we found this z in the standard normal distribution, will be easy to find the two limits of this interval. We know that z will be given by x2 bar minus mu divided by sigma divided by the square root of n. From this equation solving for x2 bar will be given by mu plus z sigma divided by root of n. And obviously x1 bar will be given in the same way. x1 bar equal mu minus z sigma divided by square root of n. This value z is called the critical value. So in this way, we can find x2 bar and x1 bar. So we have that the x bar will be between mu minus z sigma root of n and mu plus z sigma divided by root of n. And if this area is 95%, then will be a 95% probability that the sample mean will be between these two numbers. And this z will be easy to find in the standard normal distribution. In this case, we'll have a 95% probability that x bar will be between mu minus z sigma divided by root of n and mu plus z sigma divided by root of n. But these inequalities written in these ways are not so important so far, because the sample mean is something that we can get easily. So the only thing that we need to do to get a sample mean is find a sample, and from this sample obtain the mean. But why is this important? From these two inequalities here, if we take the first one, we have that mu minus z sigma divided by root of n is less than x bar. But we can solve for mu in this inequality, and we have that mu is x bar plus z sigma root of n, and mu is isolated now. If we see the second inequality, and let's take it here at the beginning. So we have that x bar will be less than mu plus z sigma root of n. But if I have that, we can also solve for mu, and this z sigma root of n that is adding at this side can be written subtracting at the other side. So will be x bar minus z sigma divided by root of n is less than mu. So now we have that this value is less than mu, and mu is less than the second value here, x bar plus z sigma root of n. So we can combine these two inequalities and write it in this way. So now we can say that we have constructed an interval around mu, and written in this way is more important because now we have an interval around the population mean. And the population mean is something that we want to estimate. And this is what is called the confidence interval of the mean. Obviously, this critical value z depends on this percent here. So if this percent is 99%, the z will be different. This percent is called a level of confidence. And this z here depends on this level of confidence. So we have constructed an interval around the parameters. And this is what we do when we are constructing a confidence interval estimate. The value z sigma divided by root of n is called the margin of error. Obviously, this margin of error will depend on z. As I told you, z depends on the level of confidence and depends also on the sample size. So if the sample size is bigger, this fraction here is smaller, and then the margin of error will be smaller. In summary, if we want to construct a confidence interval, the first thing to do is to compute a point estimate. We compute the sample mean, or in case that we want to estimate the population proportion, we found a point estimate that is the sample proportion. And around this point estimate, we construct an interval with two limits here, a lower confidence limit and upper confidence limit. And this lower confidence limit will be given always by the point estimate minus the critical value multiplied by the standard error. And in the case of the mean, remember the standard error will be sigma divided by square root of n. And then at the other side, we have the point estimate plus the critical value times the standard error. So in the case of the mean, we have the sample mean minus z times sigma over square root of n. And I'm typing here z sub alpha, just telling you that this z depends on another variable alpha. And this alpha will be the confidence level. So at the other side, we're going to have x bar plus z alpha sigma divided by the square root of n. So for the mean, we have that the confidence interval will be x bar plus or minus the critical value times sigma divided by the square root of n. This z alpha, that is the critical value, depends on the confidence level. So this alpha will be or 95% or 90% or 99%, but it's always a large number or a number close to 1. So z alpha depends on the confidence level. So that means that the z alpha, the critical value here, if we see that in the standard normal distribution, depends on how much is this alpha here. And let's assuming that this is 95%, we can use the standard normal distribution table to compute what will be the value of z alpha. Obviously, this value will be different if this is 90% or this is 99%. Let's find what will be the critical value in some cases. For example, what will it be if the confidence level is 80% or 90% or 95% or 99%? Let's compute the critical value and let's use the table. So a good idea, because the table doesn't have all this area. If we want to compute, for example, the 95% confidence interval, then we take into account that the table has only half of this area. So we are going to consider only this area, because the area in the table will be the area between the number and 0. So for that reason, if we are going to compute the 95% confidence, so I divide 95% divided by 2, just to get this area. Obviously, 95% divided by 2 is 0.475, and this is the number that I'm going to look for in the table. 0.475 corresponds to this area, 47.5. And that we need to do is just look for the closer number in the area part of the table. This will be easy because these areas are in order. For example, you can see here 0.4719, 0.4726. They are closer and closer to 0.475 until this one that is the closest one. And actually, this is exactly what I'm looking for, 0.4750. And we need to find the corresponding values for z. The corresponding value for z will be 1.9, and the second decimal is here at the top, 1.96. So the critical value when the confidence level is 95 will be 1.96. Let's do the same with the 80%. If we have the 80%, so again we divide 80% divided by 2, and it will be 0.40, and then look in the table for the value closer to 0.40. And if I see this is 0.38, 0.3907. Let's continue looking for it, and I see this is the closest one, 0.3997. So this 0.3997 corresponds to 1.28. The critical value corresponding to the confidence level of 80% will be 1.28. Let's work now with the 90% confidence interval. What will be the critical value? So again, we divide 90% divided by 2 is 0.45, and look for this 0.45 in the table. 0.45 will be 0.4495, it's really close to 0.45, and 0.4505. These two numbers are equally close. It happens, it's accustomed to use the average between the two values. For example, here it will be 1.64, and this is 1.65. So in this case, we just add and divide by 2, it will be 1.645. We do this when we know that there are two values equally close to the number we are looking for. So if the two values are at the same distance, you use the average of the z values. So in this case will be 1.645. The same happens here in the 99% confidence interval. If you divide 95% divided by 2, it will be 0.495. If we look for this 0.495 in the table, 0.495, 0.946, 0.4948, 0.4949, and 0.4951. These two numbers are equally close to 0.495, and for that reason, I'm going to add together these two numbers and divide by 2. 2.57 plus 2.58, and divide by 2 is 2.575, will be the critical value corresponding to a confidence level of 99%. Of course, we can use Excel to find the critical values. So if we use Excel, for example, take into account that Excel always gives you the whole area at the left of a number. So if we want to find the 95% critical value, or the critical value corresponding to the 95% confidence level, we add the 50% that are at the left side of the distribution. And then to use Excel to find this first number, what we are going to do is just type in whatever cell of Excel equal norm standard inverse of 0.975. This one after the comma is just informing Excel that this is cumulative. Enter, and Excel give you the same number, 1.96, rounded to 2 decimals. If you do that with the 80% confidence interval, so don't forget to add the 0.5 here, it will be 0.90, and you type in Excel equal norm standard inverse of 0.90. And don't forget the number 1. Cross bracket and press enter. And this gives you the critical value corresponding to the 80% confidence interval. It will be a good idea to solve one problem to see how to construct this confidence interval. Don't forget that we are constructing confidence interval when the population standard deviation is known. This problem says like this: assuming that the population distribution for credit card balance is normal, with the population standard deviation equal to 400. We are assuming that we know the standard deviation. Construct and interpret a 95% confidence interval estimate for the population mean balance. If a random sample of n equal 800 accounts have a sample mean equal to 2000. We are assuming that we have selected randomly a sample and the sample mean from this sample was 2000. So the information that we have from this problem is that this sample mean is 2000, and this is something we can obtain easily if we have a sample. And we also have that the standard deviation is 400 and n equal 100. So the sample size was 100. And we are going to construct a confidence interval to the mean. And we know that the confidence interval is given by x bar plus or minus the critical value times sigma divided by the square root of n. So we need to find the critical value. We are using a 95% confidence interval, and we already make a table. So this will be x bar plus or minus the critical value corresponding to the 95% confidence level. And if we see the table, we notice that this critical value is 1.96. So this 1.96 is another information that we have from this problem. Let's type it here. The critical value is 1.96. And that's it. We have everything to construct a confidence interval. And then it will be equal to 2000, that was the mean, 1.96, that was the critical value, 400, that was the standard deviation that was already known, and divided by the square root of 100. So please do that to find this number. So there will be 1.96 times 400 divided by 10, and this is 78.4. So this 2000 plus minus 78.4 is the confidence interval of the population mean. And this 78.4 is what we call the margin of error. So the margin of error is $78.40. And 2000 minus 78.4 will give you the lower bound or the lower limit of this interval. And 2000 plus 78.4, that will be 2078.4, will give you the upper bound of the interval. As an interpretation of the situation, we can say that based on the sample data, with 95% confidence, we conclude that the population mean is somewhere between 1,921.60 and $2,078.40. It will be a good idea to solve another example. The distribution of hour worked by students at the university is normally distributed. If the population standard deviation is known to be 5 hours, construct and interpret a 90% confidence interval estimate for the mean hours worked by all students at the university. If a random sample of 64 students has a mean equal to 23 hours. In real life, if we want to have an estimation of the mean hours worked by all students, what we do is getting a sample, and from this sample computing the mean. So that's what we have done, and we compute the mean of the sample, and we found that it was 23 hours. And this was taken from the sample of 64 students. So the information that we have so far is that the sample mean is 23 hours, that the standard deviation is known, that is 5 hours, and that n equals 64. We know that the confidence interval will be the mean plus or minus the critical value times sigma divided by the square root of n. Because what we are going to find is a 90% confidence interval, the formula will be x bar plus the critical value corresponding to this 90% confidence interval times sigma divided by the square root of n. And if we see the table, the critical value corresponding to 90% is 1.645. This is another information that we have from this problem, that the critical value is 1.645. And just plug all this number into the formula, and you get the confidence interval. So we have here 23 plus or minus 1.645 times 5 divided by the square root of 64. This square root is 5 over 8 times 1.645. and I found that is 1.03. So this 1.03 is the margin of error. So we have that the margin of error is 1.03. The limits of this interval are 23 minus 1.03 will be the lower limit. So will be 21.97 hours. And 23 plus 1.03 will be the upper limit of this interval. So will be 24.03 hours. So in this case, we are 90% sure. So there is a 90% confidence that the mean time worked by the students at the university is between 21.97 hours and 24.03 hours. And with that, I finished my explanation about computing the confidence interval of the mean when we know sigma. In other videos, I will be explaining how to do something similar to compute a confidence interval around the population proportion, or what to do to compute the confidence interval of the mean when we don't know sigma. Thank you.